Hello everyone. Thank you for joining our session today. My name is Alex and I am a software engineer at Line. Let me give you a brief introduction about myself. I began my career as an IT consultant about 13 years ago, and I started focusing on backend or server-side development about 6 years ago when I moved to Berlin to join the local startup scene. A little over a year ago, I had the chance to join Line and I became a member of the shop team. Now, the scope of the shop team includes any service that is required to let our users purchase and manage the stickers, emojis, and themes to be used on the Line platform. Now, included in the scope of the team is also the development of new sticker types. And sometimes during this development, we encounter very interesting challenges. So today, I want to share with you some of those challenges, how we approach them, and hopefully some of this will be helpful for your projects as well. Now, as a team, we strive to give our users more means of expression. And one way to do that was to offer customizable stickers. Now, the first product that we released in this regard was called, of course, custom stickers. Every sticker in a custom sticker product has a placeholder for one word of your choice. At the time of purchase, or any time after that via the app, you can decide which word you want to put in the stickers, for example, your name. And that word is applied to all the stickers in the set. Feel free to check out the product story in our engineering blog. And here you can see a few examples of the customized name and word applied to the stickers. Now, this product was very well received, but of course we got feedback from both internal and external users. And we thought about how to iterate over it to increase even more the customization. For example, users wanted to add more than a name or a single word to the sticker, or it felt unnecessary to change the text on all stickers at the same time. And also, users wanted to change the text more easily during the conversation. What this means is that the personalized content becomes directly part of the conversation. So for this reason, in late 2019, we started working on a new product called Message Sticker. It's basically an extension over the custom sticker concept that gives you the following feature. You have up to 100 characters per message. It allows you to input multiple lines of text. And the text edit flow, it's integrated into the chat room. What this means is that the text content becomes fully part of the conversation. And here you can see a few examples on the right. So this session focuses more on how we made this work. So let's dive in. Let's start with how we display this to the user. So the sticker, of course, has a static part, which is the main design, which has an area dedicated to the text content. Then we have a dynamic part, which is the rendered text content. And then we layer one on top of the other to get the final result. Now, this may seem very simple, but there is a lot going on behind that second step. So one of the first questions that we asked ourselves was, who generates the text overlay, the client or the server? So let's take a look. Let's start with a scenario where the client receives the style information from the server and uses them to render the text locally. Now, the advantage of this, of course, is maximum scalability, the speed of it, and because the rendering load is distributed across as many devices as needed. On the negative side, though, we have that each client needs to have access to all the resources, like the fonts used by the creators, or use web fonts on demand. And that we need to, develop and test the rendering logic on multiple platforms and devices, like iPhone, Android, desktop clients on both Windows and macOS. And we have to deal with a more complex app release process. We also need to support multiple versions of the client and OSs. And basically what this means for us is that we can have an inconsistent quality of the product, of the rendering. So let's take a look at a different scenario where the client sends the text content to the server and the server returns the rendered PNG. Well, the advantages are that the rendering engine is independent from the client device. And it's much easier to deploy new features, new fixes, or fonts to all clients at the same time. On the negative side, though, we have that we increase the computational load on the servers, so capacity planning is more complex. and we need to take care about scale in and out operations for proper resource management. And also there are some limitations in rendering libraries that we will see a bit later on. So now let's go back to the sticker composition page to see what we decided to do. So the static image that is served by a CDN can be downloaded directly by the client and cached on the device, either at the time of purchase, for example, or when receiving the sticker for the first time. The text overlay, though, will be generated on demand by the server, so that we have the advantages of server-side rendering that we showed before, and then only the overlay is transferred to the client for the final composition of the layer. Now, for that second step, the client needs to send the text content to the server. But that content is also part of a secure conversation, right? So this poses a security concern. Let's take a look at it in detail. So as we said, the text content of the rendered image is part of the context of a secure conversation. By context, we mean, for example, who is the sender, who is the receiver, if it's a timeline post, etc. And this text content should be shared between clients securely. So how do we solve this concern? Well, let's consider that the rendering server obviously needs to know the text content, but it doesn't need to know the context. So we made the server completely user and conversation agnostic. It doesn't know who the sender is, who the receiver is, or if it's a group conversation, etc. In order also to achieve that, each client needs to fetch the message overlay for itself. And it does that through a dedicated, short-lived encryption session with the rendering server. Let's take a look at how it works. Now, we start with the client requesting an encryption session to the server after being authorized by our API proxy. And then the server receives the client's public key. It generates a dedicated key pair for that session and uses it to create a decryption key. The server then stores a unique session ID with the decryption key in session storage. The server then can return the session ID, the expiration time, and the server's public key to the client. The client then uses this to generate its own encryption key, encrypts the text content, and it sends the encrypted text to the server together with the session ID. The server then fetches the decryption key from the storage using the session ID, and then renders the overlay with the decrypted text and returns it to the client for the final display. Now, this flow is executed by every client that requests an overlay. It doesn't matter if it's the sender or the receiver. Every client gets a separate session, and the server never stores the actual overlay text, either encrypted or in plain form. This means that if an attacker were to have access to the rendering server, he would still not be able to tie a specific text to a specific user in any way. Now, let's change topic and see how the overlay is actually modeled and rendered on the server side. Now, we needed a way to model and store the style information and also offer a good user experience to our creators. Already with the first custom sticker project, we had chosen SVG as a way to represent the text overlay. So let's take a look at the difference between the two. For custom sticker, users can only input one word with limited characters. So this gives us more freedom to place the text accurately. For this reason, an SVG path was the easiest choice to represent the position of the text. For message sticker, on the other hand, the text is not so limited and can be multiple lines. So the SVG path does not satisfy the requirement anymore. So we decided to use an SVG rectangle to define the area where the text will be placed. Other information that we store with the style include, of course, the font family, the colors, the outline, the direction and alignment, and for message sticker, also interline and letter spacing. Now that we have decided to use SVG, though, to model this overlay, how do we get an actual PNG image out of it? So a few considerations on the SVG format. SVG is an extensible markup language, like HTML, and over the years, it has evolved to be more easily integrated into HTML files. For example, most of the original dedicated attributes have been deprecated in favor of CSS properties. And for this reason, also, the feature compatibility depends a lot on the interpreter and the engine used and the version of the format that they apply. Now, on the Java side, we have two types of options. We have libraries like Batik from the Apache Foundation, and we have external tools like headless browsers or image manipulation tools like Inkscape or ImageMagick. We did some testing on our own, and well, Batik was the only real choice for our use case. External tools are great for batch processing, but they're too slow for near real-time rendering. So why is it faster? How does it work? Well, Batik parses the SVG elements into AWT components that respect the coordinates and the properties of the SVG elements, and then uses a Java graphics environment to render the objects into an image format. AWT, or Abstract Window Toolkit, is the Java library that is commonly used to create UI elements for Java desktop applications. Now, this works pretty well, but it does have some drawbacks for our use case. For example, it lacks the full capability of a browser environment, so there is very limited support for CSS or JavaScript inside of the SVG file. And it's also missing some locale-aware placement of punctuation characters in vertical text. And you can see a few examples in this slide. Also, the SVG implementation is incomplete and not often updated, but you can check the status of the implementation in the project's website. So let's go back for a second and take a look at the initial idea for message sticker. So the idea for message sticker was the text area will wrap and resize the text automatically to make it fit, just like PowerPoint does. The problem with that is that, well, SVG does not even support multi-line text. It only allows for absolute or relative positioning of single-line text elements. So, well, the only solution for us was to implement ourselves an algorithm to wrap, resize, and position the text elements so that they would fit the text area accurately. Let's take a look at the approach. We did some rapid prototyping, and together with the business, we decided on a few simple rules that the algorithm would follow. We were to maximize the font size, keeping the upper limit given by the style creator, and we were to prefer wrapping over resizing the font. Additionally, we were to preserve any new line characters introduced by the user itself. So let's check how the algorithm works on a few examples. In this first example, well, the text already fits in the area, so we don't need to do anything. Let's take a look at another one. In this example, though, the text is wider than the area, so the algorithm will prefer to wrap. And again, until the whole text fits into the area. Let's take a look at a different one. And in this example, now we have an even longer text. So as before, the algorithm will wrap and keep wrapping until it reaches the point where we cannot wrap anymore and the text is still taller than the area. So in this case, what we do is that we resize the font and re-execute the wrapping at the new font size. Let's take a look at the last example, where we see that the user has already split the text into multiple lines, and we have to preserve that as much as possible. So the algorithm will wrap when needed, and only then will resize the font and re-execute the wrapping so that it fits. So the algorithm works by splitting the original text in lines, calculating the pixel dimensions of each line using the font matrix classes, and then it will adjust for interline spacing and letter spacing. And then simply, if it's a line it's too long, it will wrap into a new line. If the summed heights of the lines is too high, it will reduce the font size. And it iterates until it fits both horizontally and vertically. So now that we've seen how the algorithm works, let's take a look at the whole operation on the rendering server. So as we said, the client requests the overlay, sending the encrypted text together with the session ID. The server then looks up the session ID, decrypts the text using the key found in the storage, then fetches the dimensions of the sticker based on the device, then fetches the overlay style information, which includes the position and the size of the text area, and then runs the algorithm to fit the text into the area. After that, it can compose the final SVG and then send it to Batik for the final PNG generation. It then returns the image to the client, which composes the final sticker on the device. Now, when we had this whole flow running, it was time for us to get some measurements of its performance. So we prepared a simple load test where we would send as many rendering requests to a single server using a very short text and choosing a random font. And we got some pretty promising results. We had about 300 requests per second with a very good latency up to the 95th percentile. We soon realized, though, that this was too good to be true. And as soon as we started internal user testing, we saw a different picture. So when internal users started to send the test messages, we noticed that the average latency was much higher, about 120 milliseconds, and we were serving a lower number of requests per second. And these results themselves were not bad. It was still within the SLAs that we were expecting, but it was much less than what we saw in the initial test. Well, this probably means that the initial test data was not good enough. So we went back and we executed a new series of performance tests, this time by selecting better data. For example, we picked random characters from different sets from each supported language. We picked strings with random lengths up to a defined maximum, and we chose different fonts for each language. And the results that we got were quite surprising. Not only the performance was this different from the initial test, but there was a big performance drop when changing the string length, for example, like from 20 Latin characters to 100, but also when changing language, like from 20 Latin characters to 20 Japanese or Thai characters. So we wanted to understand better which parts of the flow were affected by this. So let's go back to the server-side flow and take a look at the latency breakdown. Now, we can divide this flow into two major sections. We have fast I/O operations to fetch the data that is required for the overlay. And then we have CPU-intensive operations for fitting the text and generating the SVG. Now, if we look at the latency for the first section, we can see that fetching the data itself is negligible. It's very short time. And only the decryption of the text has more impact. And the range of values from 10 milliseconds to 34 milliseconds can be justified as, well, decrypting a longer text, of course, takes a longer time than decrypting a shorter text. The second section, though, is quite surprising. Fitting the text can take from 6 milliseconds to 151 milliseconds. And the PNG generation itself can also take from 64 to 202 milliseconds. So what is the cause of this? We tried to match it with the results of the performance test. So the first obvious thing is that, well, the number of characters in input affects the resize and wrapping algorithm. Since it's an iterative approach, it will take a few more passes for longer text compared to a short one. But also the font, the language, and the complexity of the characters affects the drawing of the characters themselves, using when rendering the SVG to PNG, for example, but also the size calculation of each character that is required for the resize and wrapping algorithm. Well, what this means for us is that, well, capacity planning is going to be a bit more complicated. So we couldn't really make very precise calculations in this regard. So we started by defining what we could consider a comfortable traffic peak. For example, we decided that we wanted each server to handle a peak traffic of 150 requests per second combined, meaning both custom and message sticker products, at about 40% of the CPU usage. And this helped us choose the specs for a single virtual machine. But then we had to make some assumptions on the overall expected traffic. For example, we assumed that we would handle as much traffic for message sticker as for the current custom sticker product. We also had to take into consideration that while custom sticker overlay can be cached in CDN due to its own specification, we cannot use caching for the message sticker due to the security requirements and the encryption in the call from the client. We also looked at the average group size on our platform, and since every client fetches the overlay for itself, well, we could expect about 5 rendering calls for each message sticker that was sent. Then we took a look at the highest peak of traffic that we had for custom sticker, which was last year's New Year's Eve, where we had a peak of 5,000 requests per second. Taking all of this into consideration, well, this could mean that we have to handle an additional 25,000 requests per second for message sticker at peak traffic. We basically would need 200 servers to comfortably handle that traffic. So, well, we reached the point of the product launch. And just to be safe, we launched the product considering the worst case scenario, so with 200 servers. After a few days, we realized that it was, of course, over-provisioned, at least for the season. And so we scaled down to 100 servers for a number of reasons, like cost effectiveness. It was not worth to keep so many servers running the whole year, especially since our traffic peaks are seasonal or at least predictable, like specific marketing campaigns or product launches or holidays. And also this would let us free up some resources for other coming up projects. Also remember that we can always scale out again if we are predicting a new peak. What we did not expect was to have memory issues. We found that we had a memory leak in our production servers. So as you can see from this dashboard, memory usage kept increasing until it reached a point where it started to swap on disk, which is bad. Now, one thing to consider is that while the virtual machine had 16 gigabytes of memory, the JVM was configured just for 8 gigabytes of heap size. So where is all this memory going? Well, we did some digging, and we found out that some font-related classes allocate native memory also for caching purposes. And due to a loop of hard and soft references, this memory is not freed correctly. So here's a rough class relationship diagram that shows the complexity of these classes that we were dealing with. But why were we experiencing this issue at this level, though? Well, the reason is that we create a new font object for every render request and for each resize of the font during the algorithm execution. Also, the caching of the related metrics, like the ones needed to calculate the text size or the glyphs to print the actual fonts, happens at a static level. And, well, we were simply hoping for the garbage collector to dispose of the objects correctly. But we were not aware of the circular dependencies that prevented it. What this also means is that, well, the testing data that we used was still not stressing the system enough, because we used a limited amount of unique characters, we chose only one font per language, and we limited the string length, leading to less resize operations. And so less native memory was used for caching. So now that we understood the problem better, it was time to fix it. So we quickly managed to reproduce the issue actually in our test environment by using the full Unicode space of characters and very long strings of random characters, and also using all available fonts. Now, for fixing the issue, we identified two options. The first one was to patch the JVM, basically by replacing the soft reference with a weak reference, because weak references can be forcibly garbage collected when necessary. Now, this worked really well, and without any changes to our code. But it has some disadvantages. Well, managing a custom patch JVM is complicated, and we would have to port the patch if we decide to migrate to a different Java version. Also, the increased garbage collection activity was causing a performance drop. Not a big one, but a noticeable one. The second option, which is what we decided to do at the end, was to refactor our code to cache the font objects that we generate ourselves. And this worked just as well as the first option, with just a slightly higher memory usage, but reduced garbage collection activity. And since we have a limited amount of font families and limited amount of font sizes, also the amount of objects that we cache is limited. Now, remember we were talking about scaling in and out the service depending on the traffic. Well, after the launch, we realized that we could improve our architecture to make it easier and faster to scale out when needed. Let's see why. So we started with a very simple architecture where the client calls a load balancer, that distributes the traffic between all the rendering servers. And each one of those servers connects to databases to fetch the style and dimension information required for the overlay. Now, those database connections are exactly what we wanted to improve because, well, some of the databases have an access control layer with IP whitelisting, which is good to have. But for every new server that we had, we need to whitelist its IP, which slows down an emergency scale-out operation. Also, each new server that we add increases the amount of open connections to the database. But the database can only handle so many, so this limits our scale-out capacity. Now, if you remember from the latency breakdown, database access occupies maybe 2% of the time spent on a single rendering. So this cannot be a bottleneck for scaling out the rendering server. So how did we solve this issue? Well, we decided to split out the database access component into its own microservice. So basically now the client connects to the load balancer, which distributes the traffic between the rendering servers, and the rendering servers themselves get the data they need from an API offered by the DB API server, which finally accesses the database. But why is this better? Well, for once, the tasks of the DB API server are very simple and fast. So we can use fewer virtual machines and with lower specs for the same amount of traffic. And also, the DB API servers hold the connection pools to the database and use caching strategies to reduce the accesses to the database. But the most important thing is that scaling out the rendering server is now independent from the DB access control layer and is not limited by the number of open connections that the database can handle. Well, what are the takeaways for us from this project? Well, in the early stages, sharing a quick prototype can greatly improve communication and help understand better the needs of the business side. And it also helped us to come up with those simple rules for our algorithm. And we also learned that real-world data, or as close to it as possible, is fundamental to properly stress test your system. What we were doing basically was a simple load test. We were not stressing it too much. Another thing is that you should be aware of the traffic patterns of your service, as it can improve resource management by scaling out and in only when needed, especially if those traffic patterns are predictable. Another thing is that you should keep in mind scalability when thinking about service architecture. It doesn't mean that we should over-engineer, but we should keep in mind how we're going to operate the service in production to make our lives easier. And most importantly, refactoring, like we did for caching the fonts, or architecture changes, like for the database access, are not only for legacy applications. So don't stop looking for things to improve in your brand new service, and don't be afraid to make radical changes after release. And this brings us to the end of this presentation. I hope you enjoyed it, and I hope that some of this can apply to your work as well. Thank you.